Combustion analysis. Yes, as stated before, combustion analysis has to do with reactions that involve combustion, fire, explosion, things like that. Giving off lots of heat. These are very exothermic reactions, and we're going to go into balancing them for the next unit when we get to reactions, but we can figure out stuff about combustion reactions. In general, they're usually going to be some kind of hydrocarbon, and we put CXHY because we don't know the subscripts because we're trying to find them through the math. Sometimes it could be an organic molecule that also has a CHO or CHN, CHS, CHClO. They could have a lot of those in there, and you're going to be basically looking at it to figure out the empirical and molecular formula of the original organic molecule that's being combusted. Now, one thing that you will notice is that combustion, of course, requires oxygen. That's the other reactant. And it takes place, like we light our Bunsen burners, we're lighting it in the presence of air, which has 18% oxygen or 19% oxygen. So there's plenty of oxygen that it can utilize for the reaction. One thing you will always note, too, for combustion reactions is carbon dioxide and water are products. Now, if you have an additional element in there, like an N or a Cl or something, you're going to get a third or a fourth product that also incorporates those elements in there as well. But for the main part, this is the general construct of a combustion reaction. Burning fossil fuels and oxygen gives you carbon dioxide and water. And hydrocarbons are basically just our fossil fuels. Okay? Natural gas, butane, octane, that's gasoline for cars. There's a whole class of compounds. The fuel number for planes and trains are a little bit different than cars, but they are all hydrocarbons. That's the basic gist of that. Now, what are we going to apply here? We're going to be using the law of conservation of mass. So what we know is matter is not created or destroyed. So if we start out with a certain amount of an element, at the end, we should also have that certain amount of that element. If it's a reactant, we have a certain amount of grams of it, then it should appear in the products at that same amount of grams. It may not be in the same compound as it was before, hence the part reaction there, but the amounts should be equal. So the amount of the reactant should equal the amount of the products. And we're going to utilize the law of conservation of mass in order to be able to apply and do all the calculations. So our first example here, an unknown compound contains only carbon, hydrogen, and oxygen. So carbon, hydrogen, and oxygen. This is on your packet, so we're going to be starting there. Okay. And it gives us a gram sample amount to work with of the compound burning in oxygen to produce this amount of carbon dioxide, this amount of water. You're going to calculate the individual masses of the carbon, the hydrogen, and the oxygen. Now, what you need to realize here is that the carbon and the hydrogen are only located in our unknown sample. Oxygen is also in our unknown sample, but oxygen is also in the other reactant, O2. So we will wait to the very end to find our oxygen because it's part of the other reactant, so we kind of have to do elimination to get down to the oxygen and be able to locate its amount. So this is kind of how it works. We're going to take our carbon dioxide amount because the amount of carbon produced in the carbon dioxide should equal the amount of carbon that was in the original compound. Okay, so let's start there. With our carbon dioxide amount is 1.9061 grams. This is kind of how it works. We're going to work this using our conversions to just carbon by itself. We're going to work it so that we get to carbon just by itself. And this is how it goes. We will change the grams, of course, into regular moles. So carbon dioxide is 44.01 if you wanted to add up the molar mass. That's another one that's frequently used, so an easily memorizable number. So we get to carbon dioxide, but I'm going to keep going. So I'm going to take this mole of carbon dioxide, put it down here, and And this is where the molar relationships start to come into play. In carbon dioxide, how many carbons are there? 1. So we can say, and this is how the relationship works, 1 mole of carbon dioxide contains 1 mole of carbon, right? Because in carbon dioxide, there's 1 carbon for every 2 oxygens. So in 1 mole of carbon dioxide, there is 1 mole of carbon. Then we can keep going, and we can do 1 mole of carbon gives us 12.01 grams of carbon. So we're working to just get the grams of carbon out of this 1.9061 number. When we calculate that, what do we get? What is our gram amount for carbon? We have 0.52, and since we have 5 digits over here in our original number, we have to keep that many, so what do we get? 0.016 grams carbon. Very good. All right, so we've done that one. Now I left you a lot of space so that you can do, the next one as well. So we figured out our carbon. Good. The next thing to do is to figure out the hydrogen. And once we figure out the hydrogen, we can take the original amount, subtract out the carbon, subtract out the hydrogen, and then we'll know how much oxygen was in the original compound. So let's do the same thing for our hydrogen. But yes, checking your answer. Yes, we are correct for the carbon. Now for hydrogen, same setup, but we're using the water amount now to work it to hydrogen. Okay, using the water to work it to hydrogen. So 0.3370 grams of water. We're going to work it over here, so we're going to use our 18.02 grams of water. That's going to equal 1 mole of water. But if you look here, in 1 mole of water, how many moles of hydrogen are in there? 2 moles of hydrogen, because it's H2O. So we have 2 moles of hydrogen for every 1 mole of oxygen in water. Then last but not least, we change that over to grams. 1 mole of H gives us 1.01 grams of H. And then out of this 0.3370, we can figure out how much of that is from hydrogen. And since hydrogen is only in the water and the original compound, we can use the law of conservation of mass and figure out that number. So what is that number? What'd you get? .0 what? 377. We have 4 digits here, so let's keep 4. And the 8 grams of hydrogen. Very good. All right, now, so we know our carbon, we know our hydrogen. If those, and we know the original compound's amount, so now we can calculate our oxygen. So yes, we are correct with our number. So let's calculate the oxygen. What was the original amount of our compound? 7540 or 90, right? This was the total grams of our unknown compound, right? So if we subtract our carbon, which was 0.52016 grams, and we subtract our hydrogen, won't we know our oxygen amount? Yes? No? Yes. So let's go ahead and take a moment and subtract those. Okay, a lot of you have calculated it.
Okay, I got the right number.
Got the right number. The right number is 0. Here I'm going to use red. 0.19696. And we're subtracting now, so we go with place value. We have 5 decimal places. Yes, it's long. I know, ridiculous number. This would be the grams of the oxygen. So we have completed A now. We have figured out our grams of our carbon in the original compound, our grams of our hydrogen in the original compound, our grams of our oxygen. So now it becomes just an empirical formula problem. Yes, they are long, and that's why there's only a few of the problems. And this basically now is going to be what you've learned. In the empirical formula, we basically found the mass. So we're skipping the percent to mass step. We have found the mass, and after that we do mass to moles, mass to moles, and then divide by small, multiply till whole. Okay, so we're going to just go, we're skipping the percent part though, but we're starting the empirical formula now. So now we need to do our little t-charts. So we have 0.052016 grams for the carbon. Change that to moles, 12.01 grams carbon equals 1 mole carbon. Then we're going to change our hydrogen over. Same procedure as before when we were doing empirical and molecular formulas. That equals 1 mole of hydrogen. And last but not least, our oxygen. (16 grams of oxygen equals 1 mole of oxygen. And now we have to do those individual calculations to find the moles. So take a moment to do that. Okay, so just check your numbers, see how you compare to my numbers. For carbon, I got, I'm going to write it up here. For carbon, it was 0.04331 moles. For hydrogen, I got 0.03741 moles. And for oxygen, I got, I'm going to put it down here, 0.0123310, and that was moles of our oxygen. Now, we've done mass to moles, we've got to divide by the smallest. Which one is the smallest moles? The oxygen, so let's divide everybody by oxygen's number. Go ahead and do that. This one obviously is going to come out to being just a 1. So that's the subscript for the oxygen. Let's divide this one. Divide by the 0.012310. And we get, for this one, we get basically 3. It's like 3.03 for its superscript. And then up here we divide it. And this one ends up being a 3.5 basically. So now what do we have to do? Since we got a 0.5, we can't have a 0.5 of an atom, so we have to multiply everybody by 2. So multiply by 2, multiply by 2, multiply by 2. So that ends up making our compound C7H6O2, right? And that is its empirical formula. This one stops at empirical formula, but other problems may ask you to find molecular formulas if they give you a molar mass of the molecular formula, like in number 2. So let's go ahead and get started with number 2. We do have plus in here, true. All right, C7H6O2. Now the next one has 4 elements in it.
No.
Compound containing carbon, hydrogen, nitrogen, and oxygen is analyzed. Now, the nice thing they do for us, let's read all the information first so we can have an idea, and it's good to underline what we have. When we have a 2.1106 gram sample is burned, that's our total amount. We get 3.2017 grams of carbon dioxide. The combustion analysis also showed that the sample contained 0.170 grams of hydrogen. So it already told us the hydrogen, we don't have to calculate the hydrogen. Yay, that's one less step for us to do. But we want to determine the carbon, so we're going to do it the same way we did before, using the carbon dioxide, working it back to carbon in order to figure out the amount in the reactant, our unknown sample. So go ahead and set that up. Grams of carbon, no, wrong number. Where's the carbon dioxide? Here it is. 3.2017. We want the carbon dioxide grams. Okay, and then 44.01 grams of carbon dioxide equals 1 mole. And it just becomes very repetitive at this point because 1 mole of carbon dioxide has 1 mole of carbon, and then 1 mole of carbon has 12.01 grams of carbon. Just different numbers, same idea though. This is how we find the grams of carbon in the original compound. And setting that up, same way that you did in the first example problem. So quickly calculate that one. So what did we get here for our grams of carbon?
We need 7372.
0.87372 grams of carbon is correct. So moving on to the next little different step here. That is the correct answer. And here for part B, they told us that when analyzed for the nitrogen content, the mass percent of nitrogen was found to be 32.16. Determine the mass in grams of nitrogen in the original compound. How would we figure this out? We have the whole total, we have the percent that is nitrogen. Change it to what? So we're going to do what
Can we
with our
just
percent?
multiply the entire thing against,
Against the what?
multiply the mass against the percentage?
Correct, but what do we do to our percent before we multiply?
And make it decimal?
Make it a decimal, thank you, that's what we're gonna do. So change our 32.16% divided by 100 so that you make it a decimal number, 0.3216. And we're gonna multiply it by our entire sample. And that'll give us, because this is the percent of the nitrogen, right? That should give us the gram amount of the nitrogen. And go ahead and make that quick calculation. Type it in and see if you get the correct answer. What'd you get? 67, and because this is 4 digits in the percent, we're going to keep it at 4 digits over here, so I'm going to round it to 88 grams of nitrogen. All right, so we figured out our carbon. Now we know the hydrogen because they gave it to us in the problem. And now we figured out the nitrogen. The last step is to figure out which element. Oxygen. So now we have to figure out oxygen. So let's go ahead and do that. We are correct. Good. We can move on. All right, so determine the mass of the oxygen now. So we're going to take our entire compound, 2.1106 grams. This is the total. We're going to subtract out our carbon first, 0.87372 grams. We're going to subtract out, let me put carbon by that so we know that's the carbon. Subtract out our hydrogen, which they gave us up here in the problem, 0.1710 grams, that's the hydrogen. And then last but not least, we're going to subtract out our gram for the nitrogen. So that's going to give us our total for our oxygen. So do that quick calculation. So when we subtract, once again, don't forget about place value here. We're going to go out only 4 digits, so we have to round to the 10,000ths. And when you do so, this number ends up being 0.3871 grams, and that's going to be for your oxygen. And then, of course, for the next part, you have to calculate the moles, because you're doing empirical formula again. So now we're back to mass to moles, divide by small, multiply to the whole. Okay, so yes, it becomes repetitive at this point. You guys go ahead and start working it. I'm going to start setting it up too on the board. You know, do your little T-charts. Okay. Alrighty, starting with the carbon. One. That's nitrogen. Which one ended up being the smallest again? Oxygen, and that's something that you'll see. Usually it's not the carbon or hydrogen that's the smallest. It's usually the oxygen, the nitrogen, or the other added elements in there. So we're going to divide everybody by oxygen's number. So go ahead and divide everybody by oxygen's number. This one obviously comes out to being a 1 for its subscript. By this one. Hydrogen ended up being a 7. Did you get a 7 for hydrogen? Divide this one. This one ends up being around a 3. And this last one over here. That one ends up being a 2, right? So our empirical formula is going to be C3H7. That does not look like a 7. Hold on. H7 N2O. Is that what you got? All right, so we have one extra little thing to do in this problem, which is because the next part, they gave us the molecular formula's mass. So this is just like before when you were doing the empirical molecular problems. You're going to find the empirical formula's mass, divide the molecular formula's mass by the empirical, and get the multiplying factor. that you multiply the subscripts by. So let's go ahead and take a look at that. So let's find the molar mass of our, it was C3H7. Why I keep wanting to make that a 2, I have no idea. All right, and 2O. So empirical formula mass, 3 times 12.01 plus 7 times 1.01 plus 2 times 14.01 plus 16. And we add all that up and we get our empirical formula's mass. And yes, you got 87.12 grams per mole. Very good. Now remember, all you have to do is take your molecular formula's mass, which is 174.2, divide it by the empirical formula's mass. And that's going to give us a multiplying factor of 2, right? So then all we have to do up here is multiply all of the subscripts by 2. So it becomes C6, H14, N4O2. And this is going to be our molecular formula. So these are the different ways and wording that they can give you the problems. It is a lot, that's why you're only assigned number 3 for homework for tonight along with your organic stuff, so keep that in mind. We will work on 4 and 5 next class.